There's a factory in New Jersey that produces 20 million Oreos every single day. That's 139,000 cookies every minute. The machines run 24 hours without stopping. The production line moves so fast that human hands never touch a single cookie from the moment ingredients enter the building until sealed packages leave on trucks. And the entire process, from flour to finished cookie, takes exactly 90 minutes. Here's how the most successful cookie in history is made at a scale that sounds impossible until you see the numbers. Oreo factories don't order flour in bags. They order it in rail cars. A single rail car holds 200,000 pounds of flour. The Mondelez factory in New Jersey receives 4 rail cars per week. That's 800,000 pounds of flour, arriving every 7 days just to keep the Oreo line running. But flour is the small ingredient. Sugar arrives in even larger quantities. The factory uses 500,000 pounds of sugar per week. That's 71,000 pounds per day. Every day, the sugar storage silos are 7 stories tall and hold enough sugar to make 50 million cookies before needing refills. Cocoa powder for the chocolate wafers arrives in 2,000-pound super sacks. The factory goes through 40 super sacks daily. That's 80,000 pounds of cocoa per day just for Oreos. Palm oil for the creme filling arrives in tanker trucks carrying 40,000 pounds each. 2 tankers per day keep the creme machines supplied. Here's what these numbers actually mean. The ingredients for 1 day of Oreo production at a single factory would fill 15 semi-trucks. The factory processes the equivalent of 300 tons of raw ingredients daily. Before a single cookie is made, the logistical operation of just getting ingredients into the building is larger than most food manufacturing companies' entire operations. The Oreo wafer dough starts in industrial mixers that look like concrete trucks but are specifically designed for cookie dough. Each mixer holds 2,200 pounds of ingredients. Sugar and leavening agents go in first. Then palm oil is added as the mixer rotates. But here's the precision required. The mixture has to reach exactly the right consistency. Too dry and the wafers crack. Too wet and they don't hold their shape. The mixers have sensors measuring resistance as the blades turn. When resistance hits a specific threshold measured in Newton meters, the mixing stops. The entire batch is rejected if consistency is off by more than 2%. The mixed dough is then pumped through pipes to holding tanks, not carried in buckets or moved on carts. Pumped like liquid through industrial piping directly to the forming machines. The pipes are heated to keep the dough at exactly 78 degrees Fahrenheit. Temperature variations of more than 3 degrees affect the wafer texture. The forming machines are where the scale becomes visible. The dough is extruded onto a moving steel belt in continuous sheets 4 feet wide. The belt moves at 400 feet per minute. That's faster than you can run. The dough sheet is perfectly uniform at exactly 0.17 inches thick. Lasers measure thickness continuously and adjust the extruder automatically to maintain consistency. The continuous dough sheet enters a rotary cutter that stamps out circular wafers. The cutter is a massive steel drum embedded with thousands of circular blades arranged in a precise pattern. As the drum rotates against the moving dough sheet, it cuts out 1,600 wafer circles per minute. But here's what happens to the scraps. To the leftover dough between circles doesn't get thrown away. It's immediately recycled back into the mixer. The factory has 0 dough waste. Every gram that enters the production line becomes part of a cookie. The recycling happens continuously in real time through a vacuum system that sucks up scraps and pipes them back to mixing. The cut wafers continue on the steel belt into an oven that's 300 feet long. Not an oven big enough for 300 feet of cookies. An oven that is itself 300 feet long. The belt carries wafers through at constant speed, while gas burners maintain temperature zones ranging from 350 to 450 degrees depending on position in the oven. The baking process is engineered down to the second. Wafers spend exactly 4 minutes and 15 seconds in the oven. This timing was determined through years of testing. and can't vary. 4 minutes produces wafers that are too soft. 4 minutes 30 seconds makes them too brittle. The 15-second window is critical. Temperature zones matter because different parts of the wafer bake at different rates. The outer edge would burn if the entire oven was 450 degrees. The center would stay raw if it was all 350 degrees. The multi-zone system brings every part of every wafer to the exact same doneness simultaneously. Coming out of the oven, the wafers are moving too fast to see individually. They're a blur of brown circles on a steel belt traveling 400 feet per minute. The belt carries them through a cooling tunnel where chilled air brings them from 450 degrees to 75 degrees in 90 seconds. Then they hit the creme application station. This is the part of the process that looks most like science fiction. The wafers are still moving at 400 feet per minute. A machine with 10 application heads deposits exactly 0.32 ounces of creme filling onto every other wafer. The heads are synchronized to the belt speed using sensors that detect each wafer's position and trigger the depositor at the exact microsecond needed. But here's the accuracy required. The creme has to land within 2 millimeters of the wafer center. If it's off by more than that, the top wafer won't align properly and the cookie gets rejected by quality control scanners. At 400 feet per minute, a 2 millimeter precision window means the depositor has 0.0003 seconds to make the decision to fire. That's 300 microseconds. The creme itself is mixed in heated tanks holding 4,000 pounds of filling. Palm oil, powdered sugar, and vanilla flavoring are blended at 110 degrees to maintain consistency that allows it to be pumped through applicator nozzles. The mixture has to be exactly the right temperature and viscosity. Too cold, and it won't pump. Too hot, and it won't hold its shape. After creme application, the belt splits into 2 levels. The wafers without creme stay on the bottom level. The wafers with creme move to an upper level. Then the 2 levels merge as a pressing station applies the top wafer to the creme-covered bottom wafer. But here's the engineering challenge. The top and bottom wafers have to align perfectly while moving at 400 feet per minute. The pressing station uses vacuum suction to grab top wafers, rotate them to match the bottom wafer's orientation, and press them together with exactly 12 pounds of force. All while both wafers are moving continuously. The pressure matters because too much force squeezes creme out the sides. Too little, and the wafers don't adhere properly. The 12-pound specification was determined through extensive testing and is measured on every cookie using force sensors in the pressing mechanism. The assembled cookies then enter the branding station. The stamps are heated to 200 degrees and press into the wafer surface for 0.4 seconds. The pressure creates the raised lettering and decorative pattern. The stamping happens on 1,600 cookies per minute. Every cookie passes through an inspection station with 6 high-speed cameras. These aren't regular cameras. They're machine vision systems that capture 500 images per second and use AI to detect defects. The cameras check for 23 different defects: cracks in the wafer, off-center creme, incomplete branding, discoloration, dimension variations, missing chunks. Each camera analyzes a different angle and aspect of the cookie. The entire inspection happens in 0.12 seconds per cookie. But here's the rejection rate. Only 2% of cookies fail inspection. That seems low until you calculate volume. At 20 million cookies per day, 2% means 400,000 rejected cookies daily. Those rejected cookies don't get thrown away. They're ground up and sold as industrial ingredients to other food manufacturers. Nothing is wasted. The cameras can detect defects invisible to human eyes. A crack measuring 0.5 millimeters. Creme, that's 1 millimeter off-center. Color variations of less than 3% from the standard. Humans couldn't maintain this consistency checking 1,600 cookies per minute. The AI never gets tired, never loses focus, and never lets a defective cookie pass. After inspection, cookies move into the packaging area. This section of the factory is under positive air pressure, meaning air flows out when doors open, not in. This prevents contamination from outside air entering the packaging zone. The cookies are arranged into rows of 3 by mechanical arms. The arms use vacuum suction to grab cookies from the main belt and place them into sleeves. The sleeves are preformed tubes of plastic film that the cookies slide into. Then the sleeves are sealed on both ends using heat sealers that melt the plastic shut in 0.3 seconds. Multiple sleeves are then grouped into larger packages. The standard package contains 3 sleeves for a total of approximately 36 cookies, depending on product variation. The packages are formed, filled, and sealed in a continuous process that handles 800 packages per minute. But here's what happens before sealing. Each package is flushed with nitrogen gas. This isn't for show. Nitrogen displaces oxygen, which causes fats to oxidize and go stale. By removing oxygen and replacing it with nitrogen, the cookies stay fresh for up to 9 months unopened. Without nitrogen flushing, they'd go stale in 3 weeks. The sealed packages then go through metal detectors. Every package, the detectors can identify metal fragments as small as 1 millimeter. If metal is detected, the package is automatically ejected, and the entire batch from that production run is held for investigation. This happens despite all ingredients being screened before entering production, because metal can enter from equipment wear. Let's put the full production scale in perspective, because the numbers sound fake until you calculate them out. The New Jersey factory makes 20 million Oreos per day. That's 7.3 billion cookies per year from one facility. Mondelez operates 6 Oreo factories globally. That means global Oreo production exceeds 40 billion cookies annually. If you lined them up edge to edge, they'd circle the Earth 62 times. If you stacked them, the stack would reach from Earth to the moon and back. Twice. But here's the part that breaks your brain. Every Oreo you've ever eaten was made in one of 6 factories. Every single cookie follows the exact same 90-minute process we just described. The consistency is so precise that an Oreo made in New Jersey tastes identical to one made in China or Mexico. The machinery is calibrated to tolerances measured in milliseconds and millimeters to ensure this. The factory never stops. Machines run 24 hours a day, 6 days per week. Sunday is for maintenance. During the other 144 hours of the week, production is continuous. Workers operate in 3 8-hour shifts, but the cookies don't care what shift it is. The belt moves at 400 feet per minute regardless of whether it's 3 a.m. on Tuesday or 2 p.m. on Friday. From the moment flour enters the building until packaged cookies leave on trucks takes 90 minutes. 90 minutes from raw ingredient to finished product. This is achieved through continuous flow manufacturing, where materials never stop moving. There are no breaks in the process. Dough mixing flows directly to forming. Forming flows directly to baking. Baking flows directly to cooling. Cooling flows directly to crème application. Every step is synchronized to the same belt speed, so there's never a backup or bottleneck. But here's the logistics nightmare behind this. Ingredients have to arrive precisely when needed. Too early, and you're storing excess materials. Too late, and production stops. The factory uses just-in-time delivery systems where suppliers deliver ingredients the same day they're used. A rail car of flour arrives, gets unloaded directly into silos, and that flour is being mixed into dough within hours. The factory produces 0 inventory of work in progress. There's no warehouse of half-finished cookies waiting for the next step. Everything is always moving. The only storage is for finished packaged products waiting for shipment. This efficiency means the factory can produce 20 million cookies per day using only 180,000 square feet of building space. That's 111 cookies produced per square foot per day. Compare that to traditional batch manufacturing, where products sit in storage between process steps and you'd need 5 times the space for the same output. The precision and consistency of industrial production is why Oreos taste identical whether you buy them in New York or Tokyo. Every factory uses the same equipment calibrated to the same specifications. The dough mixing ratios are identical. The oven temperatures are identical. The creme formulation is identical. But here's what people don't realize. This consistency isn't automatic. It requires constant monitoring and adjustment. Every batch of flour has slightly different protein content. Every shipment of cocoa has slightly different fat content. The machines automatically adjust mixing times and temperatures based on ingredient variations to produce the same result every time. The factories employ food scientists who do nothing but monitor production consistency. They test cookies from the line every hour. They measure moisture content, sugar concentration, fat ratios, and 30 other parameters. If any measurement drifts outside acceptable ranges, they adjust the machines immediately. This is why generic store-brand sandwich cookies never taste quite like Oreos. It's not the recipe. Oreo's recipe isn't secret. It's the precision of industrial production at massive scale. Generic brands can't justify the equipment investment to hit the same tolerances. Their cookies vary batch to batch. Oreos don't because the machinery costs $50 million per production line and is calibrated to specifications that cost another $10 million per year to maintain. The Oreo factory is a case study in how modern food manufacturing has become more like semiconductor fabrication than cooking. The precision rivals electronics manufacturing. The quality control matches pharmaceutical standards. But here's what it means for the cookies themselves. They're not made by bakers. They're made by chemical engineers who optimize recipes for machine compatibility. The dough isn't designed to taste good first. It's designed to flow through industrial piping at consistent viscosity, extrude at uniform thickness, and bake to precise moisture content. The fact that it tastes good is secondary to the fact that it processes consistently. This is why artisanal bakeries can't compete on price. A bakery making cookies by hand might produce 500 cookies per day. The Oreo factory makes 20 million. The economies of scale are so extreme that Oreos cost less per cookie than the raw ingredients cost for handmade cookies. When you're buying flour in rail cars instead of bags, your ingredient cost per cookie is measured in fractions of a cent. The success of Oreos isn't just good marketing or a great recipe. It's industrial engineering taken to an extreme that produces consistent quality at impossible scale for prices that make competition economically unfeasible. The factory is optimized to a degree that most manufacturing industries don't approach. That's how the world's #1 cookie is made. Not in a kitchen. In a machine that processes 300 tons of ingredients daily into 20 million identical cookies through a 90-minute continuous flow process optimized by decades of engineering and billions of dollars of equipment investment. And it never stops.